In this video, we'll be looking at solving logarithmic equations. Logarithmic equations are actually a lot easier to solve than that of exponential equations in some cases. In most cases of solving logarithmic expressions or equations, all you have to do is change the form from a log equation into an exponential equation. So for this particular example, all we're going to do is we're going to just change the form. We'll notice that the log expression is all by itself already, allowing us to easily change the form. First thing I'm going to note is the base of this log is 2. I know that every log is equal to an exponent, so the exponent on that base is 3. And then everything inside that log becomes the other side. So again, base of 2, every log is equal to an exponent, so 2 to the power of 3 equals to the x minus 4. Well, 2 to the power of 3 is 2 times 4, 2 times 2 is 4, times 2 is 8, 8 equals x minus 4, and therefore if I'm adding the 4 to the other side, I get x equals to 12. And that's it. That's how to solve a logarithmic expression, logarithmic equation. All you have to do is change the form. Now, the problem, however, with these log equations is that you do really have to check them. Regardless of whether the problem tells you to or not, that x value could fail to check in this log equation, very much like that of a radical equation and a rational equation. And those are the two functions that have domain issues. So those are the two functions that you're going to really have to evaluate to check. So log included with that has domain issues and therefore should be checked as well. So if I plug this 12 back into here, I'm going to have log base 2 of 12 minus 4. Well, 12 minus 4 is 8, and log base 2 of 8. Now I'm going to go ahead and ask myself what power of 2 gives me 8, and the answer is 3. And sure enough, that answer is going to check. So again, you need to, every single time you solve a logarithmic equation, you need to check it. And at the same time, to solve a logarithmic equation, all you need to do is get the log by itself and change its form. So the next example we're going to look at is going to be 4 times the natural log of 3x equals to 8. So you'll first notice that, well, wait a second, the log isn't actually all by itself. There's something outside of the log but next to it. Well, that 4 times, I'm going to go ahead and instead divide that 4 away from the natural log. There's other ways that you could handle that power, or that 4 there. Notice how I called it a power. I called it a power because technically that 4 can be pulled into the log as a power of everything in here. But I think that's going to make the problem more complicated than less complicated. So in this case, I'm going to get 8 divided by 4 is 2. And now when I change the form, I'm going to have e as my base because it's natural log. The log is equal to the exponent is 2, and this is equal to 3x, and therefore x is equal to e to the power of 2 all divided by 3. And that's it. That's the problem. That's all we have to do. If I take this and I plug it back into the original, again, the original being 4 times the natural log of 3 times my x value now being e squared divided by 3, this is supposed to be equal to 8. Well, 3 and 3 will cancel each other out. I will have the natural log of e squared. What power of e gives me e to the power of 2? Well, it's 2, so it's 4 times 2, and therefore gives me 8, and sure enough, that answer is going to check. Now again, keep in mind that it's not always the case that these things are going to check. There are some situations where if we attempt to check them, they come out as not valid solutions, in which case, again, we should write no solution as the solution. But again, for these particular cases, the goal is to get the natural log by itself or the log by itself and then solve. So the next example we're going to look at is going to look like this. I'm going to have log of x plus log of x minus 3 equals to 1. And again, keep in mind that those parentheses are there. They have to be there for it to include that minus 3 inside the log. So now the question is how do I solve something that has multiple logarithmic equations? Well, if there's a constant or some other variable sitting outside the log, your first goal is to see if we can smash these two logs together. If they're on the same side, we might as well try and get them together anyways, especially if they have the same base. To combine these two logs together, the addition sign tells us that we're going to multiply their insides. So I'm going to have log of, just like the product rule says, x times x minus 3 all equals to 1. And now that there's only one log and the log has nothing else with it and it's all by itself, nothing on the outside, I can go ahead and change the form of this log to be exponential. The base of this log is 10. The exponent is 1. Don't forget that that exponent is just changing the form. And then this is equal to, again, this side all by itself. So x times x minus 3. Now there are other ways to view this process, but I think that those other ways are slightly more confusing. I will go ahead and write it here off to the side, is that technically what we're doing is we're taking the exponential form and we're putting a base underneath those two sides. It's really the opposite step of what we do with the exponential equations, where we drop the base, it goes to here. Well, we're adding the base now, and the two sides become the new exponents. Now the reason why I find this a little bit more complicated is because 10 to the power of log base 10 of x minus 3, this should be understood as x times x minus 3. But a lot of cases it's difficult to remember that particular rule from the original starting point of logarithmic expressions. But in any case, we get to here, so 10 to the power of 1 is simply 10, and we get x squared minus 3x. I can go ahead and subtract the 10 and get 0 is equal to x squared minus 3x minus 10, and I can solve this like any other quadratic. In this case, it does factor into x minus 5 and x plus 2. And I can go ahead and get the answers as x equals to 5 and x equals to a negative 2. Now again, when I'm done with this particular step, I do need to go back and I need to check my answer. This is where the steps can cause problems. Combining these two together change this addition problem to a multiplication problem. This multiplication problem allowed there to be other values inside that might not have been allowed before. But if I were to take this negative 2 right here and I plug it back into this, I'm going to have log of a negative number plus log of another negative number, and that doesn't make any mathematical sense, because remember, the domain of any basic log function is going to be x has to be greater than 0. Can't have equal to, can't have negative. So the negative 2 in the original problem won't check. You'll notice that in this here, it will, because a negative 2 times a negative 5 is a positive 10, and log base 10 of that is going to work fine. Now, if I go to plug in the 5, it might be more difficult to see it, but I'm going to have log base 10 of 5 plus log base 10 of 2. And if I were to go ahead and chuck those into a calculator, you will get the value of 1 coming back as the correct answer. So that covers your basic logarithmic equations. In almost all cases of the examples, what you're going to do is you're going to get it to be one log expression, and then you're going to go ahead and change the form from log to exponential. One more example that doesn't necessarily follow this rule but does enforce it is the natural log of x minus 3 equals to the natural log of 7x minus 23 minus the natural log of x minus 1. And the reason why it doesn't, again, follow this rule but does enforce it is because we're still going to go ahead and do our best to get both sides to have a single logarithmic expression. I could go ahead and take this side and just subtract it over and then can make it all one giant log, but I think in this particular example it makes more sense for us to just simply combine these two. So I'm going to have the natural log of x minus 3 equals, because there's a subtraction sign between these two log functions, I'm going to combine this together using the quotient rule, where the positive log function goes on top and the negative one goes on the bottom. And again, notice how they combine together. This subtraction identifies which log is on top, which log is on bottom, but there's only one log altogether, just like the quotient rule says. Now that I have log of this equals log of this, just like we did the concept of the exponential functions where we drop the bases, well, if this side has a log and this side has a log and they're the same base, then I can assume that the insides must be exactly the same. This is a basic rule of some algebraic properties. So now that we're here, I'm going to solve this rational equation, because that's what we've turned this into. There are other ways to do this problem. We could have simply added the natural log of this over to the other side, but you'll notice here that if I do that, then it's going to change to a log of this plus the log of that, and then they're going to combine together to be a log of multiplication. Well, if I try to solve this rational equation, I'm going to have to take both sides and multiply by this common denominator of x minus 1, which is the exact same thing. So no matter how you do this, no matter what step you take first, you should end up concluding that we're going to have some kind of quadratic. X squared minus 4x plus 3 equals to 7x minus 23. If I go ahead and add the 23 and I subtract the 7, I'm going to get x squared minus 11x plus 26 equals to 0. Now if I do some quick math off to the side here like I normally try and do, I'm going to try and multiply to get 26 but add to get a negative 11. I need two negatives or two positive numbers to do this. I don't think that's going to happen because it's 1 and 26 or 2 and 13. And 2 and 13 would work if this number was a negative. Because then I could make this a negative and that a positive. With that being said, it doesn't look like this is going to work for us in terms of these problems, which means that I'm going to have to go ahead and solve this using the good old quadratic formula. So we're going to go ahead and do negative b, so negative 11 plus or minus the square root of b squared, so negative 11 squared, minus a 4 times my a, which is 1, times my c, which is 26, all divided by 2 times a, 2 times 1. I'm going to get a positive 11 plus or minus the square root of some number divided by 2. That some number, I'm going to go ahead and see this as a positive 121 off to the side. That's 11 squared. And 4 times 25 would be 100, so 4 times 26 would actually be 104. So minus 104. In this case, I'm going to have, looks like a positive 17 underneath that radical, and that looks like a valid answer. Not a nice answer, but a valid answer. Now the question comes down to, well, how the heck do I check this? Well, this is where, again, you're going to go straight to your calculator, and what I would do is I would go ahead and evaluate x minus 3, where x is going to be this whole thing. Skipping the plus or minus, I'll do the plus first. So I'm going to go ahead in here very carefully. I'll just type in the first setup of it. It's going to be second natural log of my x value being in very careful parentheses, 11 plus the square root, where's my square root button? Square root of 17. That whole thing divided by, so I'm going to be very careful with this, making sure that that whole thing is in there. Yep, divided by 2. And then I'm going to go ahead and put that in extra parentheses because I don't want to make any silly mistakes. And then I'm going to go ahead and add to that plus 3. Sorry, minus 3. It's minus 3. That would be a terrible mistake to make at this point in the problem. End my parenthesis, and then hit enter. You'll notice here that it does validate what we have and show us what it is clearly. This minus 3, if I were to combine it into a common denominator, I would get that plus 5. I'm going to hit alpha and enter to make sure that it approximates it, and then I'm going to do the exact same thing for the other side. And again, yes, you have to type it into this one, then subtract it from this one, and you have to do it very carefully. Try not to use the approximated form of that value. So if I do 11 plus the square root of 17, and I take that value as a whole, and I divide it by 2, don't use an approximated form of this, because the 7.56155, if you cut it off somewhere, it's not going to be exactly the same when you type it into these things, which means that you might not get the exact same thing on both sides. Now, you could cut it off at a certain number of decimals and then hope to God that it's going to be accurate up to those certain number of decimals, but that's probably not the safest move. What you could do instead is take this value, and I'm going to hit this STO button, and I'd store it into some other variable number. Let's go with h, because I probably haven't used h in a while. So I'm going to store it into h. Now anytime that you do this, you can simply go ahead and do second natural log of h. Let me go alpha h, and then minus 3. And if I don't get the same number, then I've done something terribly, terribly wrong with this problem. If I do alpha enter, sure enough, 1.51766, and that didn't come out the same. And I'm not sure why it didn't come out the same, because something's not right. Oh, I know why. Because I stored the... no, that's the solution. I'm not sure exactly why that came out as wrong, because this right here is the same thing as this right down here. So that should come out as the same number, and I'm not exactly sure as to why it's not coming out as the same number unless I'm typing something in incorrectly, which is possible here, but I'm just not seeing it. It's that right there. No, it's right there. Oh, there it is, right there. Okay, so there's your final solution, 1.517. That's with the subtraction by 3. And if I scroll all the way down here, sure enough, it is the same thing. So I didn't make any mistakes. I just thought I did because I'm blind as a bat. But in this case, that's how you were to solve equations like this, where the quadratic formula is part of your solution set, and then you're going to have to go back through and check those values. That's the most efficient way to check them, is use that store function. I would store 2 separate answers, one in h and one in something else, or one in any other number, so that you can very easily see what you're working with. But that's going to end this video because it's already been pretty long, but be very careful when solving logarithmic equations.